Right, today we're going to talk about the central limit theorem. The central limit theorem is the most important theorem in all of statistics. We wouldn't have a class without this theorem, so you need to make sure you get it really good on this video. Maybe watch it more than once. How shocking would that be? But it would really help you. Central limit theorem. Before I even go into what it is, it's all about x bars. It's all about x bars. I need you to remember what x bars are. X bars are sample means. They're all about sample means. We're going to talk about sampling distribution again like we did yesterday, but the sampling distribution we're talking about today is only x bars. Sampling distributions with x bars, the sample means, not the sampling distribution itself, but sampling distribution of the x bars, of the sample means. Keep that in mind. We're talking about the sample means. All right, the central limit theorem tells us that for a population with any kind of distribution, the distribution of the sample means, that's the x bars, approaches a normal distribution as the sample size increases. The bigger the sample size gets, the more normal the distribution of sample means gets. The procedure in this section forms the foundation for estimating population parameters and hypothesis testing, which is where we're going very soon. Okay, a couple of givens here with the central limit theorem. First of all, the random variable x has a distribution, which may or not be normal, with mean mu and a standard deviation sigma, which you know that already. Those are the symbols we use. The random variable has a distribution. It does not have to be normal. But look at number 2. Simple random samples, SRSs, which we talked about a long time ago, of all the size n, are selected from the population. Those are the two givens. Now, if you forgot what simple random sample is, here it is right here. The samples are selected so that all possible samples of the same size have the same chance of being selected. So every single possible sample of the same size has the same chance of being selected. That's what an SRS or simple random sample is, and we talked about that a long time ago. And these are, don't forget, mean, mu, standard deviation, theta of the population. All right, more stuff. Conclusions about the central limit theorem. These are huge. Make sure you get these. The distribution of sample mean x bar will, as sample size gets bigger, approach a normal distribution. So the bigger your sample size, the more normal it becomes. That is the distribution of the x bars, the distributions of the sample means. The mean of the sample means is the population mean. So whatever the mean is in our distribution of the sample means, that is always equal to the population mean. This is big down here, number 3. The standard deviation of all sample means, of all the sample means, is not just sigma, but sigma divided by the square root of n. N is the size of the population, so you take the square root, size of the sample. Sorry about that. N is the size of the sample, so you take the square root of the size of the sample. All right, practical rules commonly used. Number 1, for sample sizes n larger than 30, okay, that's going to be our big number right there. If the sample size is larger than 30, the distribution of the sample means of x bars can be approximated reasonably well by normal. So anything bigger than 30, we're going normal distribution on it for x bars, for sample means. The approximation becomes closer to normal, the bigger it becomes. So 30 is going to be our cutoff right there. So if we see a sample size bigger than 30, we're going normal. We're going to assume it's normal. That's the best approximation. Number 2, if the original population is normally distributed, if the population is normally distributed, then for any sample size, the sample means will be normally distributed, not just bigger than 30. So if they tell us already in the problem that it's normal, that the population has a normal distribution, and we have a sample size like, let's say 20, we're still going to use the normal distribution because it tells us the population is normally distributed. Now, it can tell us the population looks like anything, and if our sample size is bigger than 30, then we're going normal. So 2 cases. If it's bigger than 30, sample means normally distributed. If the population is normally distributed, sample normally distributed, sample means. All right, notation, all this stuff is so important. The mean of the sample means, symbol is this right here, mu of x bar, mu x bar. That's the mean of the sample means. The standard deviation, same deal. Standard deviation x bar, standard deviation of the sample mean, population standard deviation divided by the square root of the sample size. That's the standard deviation is also called the standard error, which we'll get to very soon exactly what that means. But think about what standard deviation means. It means, distance away from the mean. So that means, if we take a sample and it's not exactly the mean, if it's a standard deviation away, it's actually an error, a little bit of an error because it's not exactly what the mean was. So that's what's called the standard error instead of standard deviation. All right, let's look at an example here. Watch what happens as we go for normal sample size. Let's say we take one sample and it has a normal distribution. Okay, so look what happens when we take 10 samples of the same size and then take 50 samples of the same size. Now these are all the X bars, right? These are the mean of the sample distribution, and the closer, the bigger your sample size, the more normal it becomes. So like this one says each dot represents 11 observations, so that's a lot. Okay, what if it's uniform? Uniform means, like rolling a die, and you have the same chance of getting same number, each number, 1 through 6. So uniform, if you just take one sample, it looks what it looks like. That's uniform, everything's the same. But if you get 10 all of a sudden, it's starting to look more normal. If you go to 50, all right, the sample means, look what happens. And remember, these are sample means, distributions of sample means. I keep saying that because I need to drill that in your head that we're talking about sample means only. And last of all, what if you get a U-shaped distribution? We have one sample here, and it's a U-shape. It's like an upside down bell curve or upside down normal distribution. But look what happens once you take 10 samples. Sample size of 10 instead of sample size of 1. When you take a sample size of 10, all of a sudden, look what's happened to that U-shape. Sample size 50, and remember, these are sample means. The mean of the samples all of a sudden become very, very normal. So I'm trying to drill this in your head. The bigger your sample size, the more normal the sample means become. 30 is our cutoff. If we get a sample bigger than 30, then we're going to say, okay, we're going to use the normal distribution. And less than 30, we still can use it if the population has a normal distribution. Very important point. This is what I've been saying the whole time. As the sample size increases, the sampling distributions of the sample means approaches a normal distribution. So the bigger the sample, the more that your sample means approach normal distribution. Let's look at an example here about elevators. Suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assuming a worst case scenario in which the passengers are all male, that would be terrible, 16 males in an elevator, what are the chances the elevator is overloaded? I'd say pretty good. Assume male weights follow a normal distribution. Okay, they tell me that the population of male weights are normally distributed. So I'm using the normal curve here, with a mean of 182 and standard deviation of 40.8. Okay, first of all, part A, find the probability that one randomly selected male has a weight greater than 156.25. That's what we've been doing all along, so I'm going to do that first. Part B, find the probability the sample, that's different, of 16 males have a mean weight greater than 156.25, which means it would exceed 2,500 pounds, which means bad news for those on the elevator. So I'm going to show you how both of these work. The difference being these problems, this is a huge difference. One is just for one randomly selected male. The other one is a sample. And the reason I can use normal distribution for part B is because it told me up here that it was normally distributed. If it wouldn't have said that with only 16, I couldn't do it. I need a sample size 30 or larger, but because it told me in the problem it was normal, I can use normal distribution. Okay, part A. Find the probability that the selected male has a weight greater than 156.25. So I'm going to do what we always do. All right, I found the z-score. There's your z-score right there. Drew the little graph down here. It looks just like that. So I need the probability of all that area in there. Now, of course, in your calculator or your technology on StatCrunch, you could punch in your x, you could punch in your mean, you could punch in your standard deviation, and it's just going to tell you this. It's going to tell 0.7422. So a male, basically 74% of males' weight is greater than 156.25, that's most of them. That's definitely majority. Okay, let's look at part B. Part B, find the probability of the 16 males, that's your sample. Okay, now, anytime you're dealing with samples, you have to change your standard deviation. Your mean is still the same. We write it a little bit differently. But your standard deviation, you must take your original standard deviation divided by the square root of the sample size to get your new standard deviation. So that's going to change your z-score pretty significantly, and also or change what you punch in. But if you're dealing with a sample, you must change your standard deviation. So punch that in. There's my green area. I'm looking for the area in there, and so I think it's on the next slide. What was it on? Yeah, it's on the slide. So part B, there's a 7.7432 probability that any given male weigh more than that weight, but there's this big of a probability that the sample of 16 males together will have that weight or bigger, which means if it has 16 males in there, there's a very good chance that weight of 2,500 will be exceeded. Like that kind of chance, like 99.55% chance that, there's too much weight in that elevator. And knowing the guys, they probably would stay in there anyway and just test it out to see if it would work. But glad I'm not on it. But anyway, that's how it works. So the difference being an individual like we've been doing versus a sample, and you must change your standard deviation. But please make sure you can use a normal curve to do it. And again, the two cases are if they tell you the population is normally distributed, or if the sample size is bigger than 30. And don't forget, this is only for sample means. Only for sample means. All right, and we're going to skip this last slide. I don't think we're going to need this. If we do, we'll come back and hit it later. So I think that's good enough. Go back and watch them if you need to. Make sure you get the question at the end. I'll see you tomorrow.